Hello everyone, my name is Dr. Raj Dasgupta. I am a computer engineer at the Naval Research Laboratory in Washington, D.C. This is part of a 3-series lecture that I'll be doing with the TJ AI ML Club. The general topic of this lecture series is game theory and reinforcement learning. In the first topic of this lecture, I will talk about introduction to multi-agent decision making via game theory. The second topic will be on advanced reinforcement learning algorithms, and the third topic will be on game playing AI, which will connect the game theoretic techniques that we talk about with the reinforcement learning techniques that we discuss. Basically, we will look at the algorithms like AlphaGo, AlphaZero, and so on that are used to play computer games these days and connect them with the results of game theory that we learn. Our first lecture is on the topic of game theory. This is the outline of the lecture that we will have. I have divided the lecture into 4 different parts. Each is about 8 to 10 minutes long. I start off with a brief history of game theory, and then I get into the details of games, like the main concepts, action strategies, how to solve games using Nash equilibrium, and then we will wrap up with a review of game theoretic software. I've given some additional topics at the end. Feel free to review them later on. And as ever, if you have any questions, feel free to email them to me or ask me after this lecture. So I'll wrap this introductory discussion up with a brief history of game theory. So the field of game theory has been in existence with the name game theory for about a century now. So von Neumann first did some work on the topic of utility theory. It laid down the foundations of math analyzing 2-player games. That's when the work on game theory started. John Nash has been very instrumental in promoting this field. His Nash theorem and Nash equilibrium basically expanded the field to a great extent. A lot of work started happening in the field of economics. Then in the 1970s, topics like evolutionary game theory, learning in games came. And finally, the final turn came in the 1990s when computers came around and the field of computational game theory, software agents to solve game theoretic algorithms came around. So these are the names along with pictures of a few well-known game theorists, John von Neumann, John Nash, you already must have heard their name, several others, Harsanyi, Meyerson, Morgenstern. Feel free to look up their names on Wikipedia and see what their contribution to the field of game theory has been. So I'll stop here for this introduction, and then our next topic will introduce game theory through simple games. We now start with the second part of our lecture on simple 2-player games. In this part, we will talk about normal form games and the main concepts inside games, namely action strategies and the payoff metrics. We start with a simple game. We have 2 persons, also called players. Their objective is to cross a bridge over a river. There are certain constraints in the game, which is the bridge can hold only 1 player or person at a time, and the players cannot also see each other from across the bridge. Each player has a set of actions. In this example, each player has 2 actions, namely go and stop. This is called the action set of the player. Each player's objective is to select one action from the action set. And by doing the action, the player gets a certain payoff or utility. In our example, the payoff for the action go is +1 and the payoff for the action stop is -1. Note that both players have the same set of actions and also the same utilities or payoffs for their actions. We will also assume a rationality assumption, which is each player selects an action that gives the highest payoff. Now, I introduce this setting just to make you familiar with what the different components inside a game are. What actually happens is each player's action is not just a single action. Rather, each player's action or decision to select an action depends not only on its own action, but also on the actions of the other player. In effect, what we end up having is joint actions. It's sort of like correlated actions, but they are called joint actions in the context of game theory. The joint action of the game is essentially the cross product of the action set for each player. So in our example, the joint actions would be go, go, stop, and so on. Now the payoffs of the player get associated with the joint actions as well. For example, for the joint action go and go, player 1's utility is the first component here, which is -2. Player 2's utility is the second component, which is -2. This corresponds to the definition of the game, which is if both players get on the bridge at the same time, given the bridge can hold only one player, they end up getting a utility of -2, also called a disutility. Similarly, when both of them stop, because their objective is to cross the bridge, they don't get anything out of it. Their utility then becomes -1 for the first player and -1 for the second player also. Note that when one player plays go while the other player plays stop, the player playing go crosses the bridge and gets a positive utility, whereas the other player which did a stop, that gets a negative utility. Now, in this slide, we wrote the payoffs in the form of equations for each joint action with numbers. It is much easier for a person looking at the game to look upon these payoffs in the form of a matrix. The structure of the matrix basically captures the joint actions. So the rows of the matrix give the actions for the first player. Columns give the action for the second player. In our example, the first player's actions were go and stop, and the second player's actions were also go and stop. The joint action go corresponds to this cell out here. And remember from the last slide, the joint action go gave a utility of -2 to the first player, utility of -2 to the second player. And that's what I write in the go, cell of the payoff matrix. And similarly, I fill up the rest of the cells of the payoff matrix. Okay. So basically the payoff matrix allows me to represent the game in a very compact form. The main problem in game theory, said simply, is this, which is given that each player knows the payoff matrix. In other words, it knows the actions and payoffs of itself and also of the other player. How can a player individually make a decision or select an action that will be the best for itself? The term best is loosely defined. It could either mean to minimize regret, it could be maximize the sum of the payoffs. Basically, it depends on how we are solving the game. Or, as I say in the last bullet out here, the way we solve the game could be to find a stable or equilibrium action. Stable action means basically if a player changes or deviates from that action by itself, its utility or payoff will go down. In other words, there is no incentive of deviating to a different action from a stable action. Now, this concept of stable action is very important in the context of game theory. It's also known as the well-known Nash equilibrium. We will revisit this when we talk about Nash equilibrium again in the next part. Okay. For the time being, let us tie what we just saw in the context of a simple game to multi-agent decision making. So in our 2% crossing the bridge game, the players were actual people who were crossing the bridge. When we have computer programs running game theory algorithms, instead of people making decisions, it's actually the agents, software agents, which are running the computer algorithm, which makes a decision. For example, Nash equilibrium outcome or whatever outcome you choose for the game. Okay. So the main problem reinstated in terms of agents is when two agents interact, what action should each agent take? And of course, we have our assumption, which is very important in the context of game theory. It's sort of the bedrock of game theory, which is we assume that like the humans, agents are also self-interested, or in other words, they behave rationally, or each agent takes an action that maximizes its own utility or its own payoff or benefit. Okay. So now, let us wrap up by formally defining a game, which is the normal form game has three components: the number of players denoted by n, the set of actions of the players denoted by a, and the utilities of the player denoted by u. If we have a two-player game, the set of players is player 1 and player 2, and by convention, player 1 is the row player, player 2 is the column player. A is the set of actions, and for a two-player game, A1 denotes a set of actions for player 1, for example, go or stop. Similarly, A2 is a set of actions for player 2, and the joint action given by capital A is A1 cross A2. The example for the crossing bridge example is shown here. U is the set of utilities. For a two-player game, once again, U subscript 1 denotes the utility to player 1. And utility, remember, corresponds to a joint action. So utility is indexed by A1, A2, which is the action for the first player, action for the second player, together giving the joint action. And similarly, the utility for player 2 is U sub 2. You can refer back to this game and see that utility for player 1 for the action go, stop, which is go for player 1 and stop for player 2. Utility of player 1 is positive 2, as I show out here. And this form of a game, where I have the players represented as the row player and the column player, the actions for the row player and the column player along the rows and columns, and the utility values of the players given inside the matrix in the form of payoff matrix. This form of a game is called a normal form game. And they are represented on paper using a utility or payoff matrix. Finally, I would like to just clarify some terms. Remember that the normal form game is a single shot game, which is it's only played once. It's not repeated. Going back to the bridge example, in our case, each player would cross the bridge just once and the game would end. By that I mean either they go, or go, stop. Whatever the action they take, they do it once and the game is over. Also, the game is simultaneous move, which is players move at the same time. It is not a sequential game, which is each player cannot see the opponent's move before selecting its own move. Once again, going back to the crossing the bridge game, each player is deciding whether to go or stop at the same time. This is in contrast to board games like chess, where you have sequential moves. Player 1 makes a move, player 2 looks at the move of player 1 and then makes it move, and so on. Our game right now, the normal form game, is a simultaneous move game. And finally, each joint action results in a different outcome of the game. So selecting a joint action is akin to saying selecting an outcome of the game. I've shown the outcomes corresponding to go, stop, and stop, go by these arrows here. Okay. So at this point, we have seen how to take the description of a game and represent it in the form of a payoff matrix. Our next topic will be to use this payoff matrix and calculate the Nash equilibrium. Now we start with the third part of our lecture, the topic of Nash equilibrium. We will study this in the context of a well-known game called a prisoner's dilemma game. So the statement of the game goes like this. Two persons are charged with the same crime and held in separate cells. They have no way of communicating with each other or making an agreement beforehand. They are told at the same time that if one of them confesses the crime and the other does not, the confessor will be freed while the other person will get a term of 3 years. If both confess the crime, each will get a term of 2 years, and if neither confess the crime, each will get a 1-year term. Now let us see how we can take this game statement and convert it into a normal form game represented as a payoff matrix, which we saw on the last part. Okay. So remember, the normal form game has 3 components. The first component is the set of players. Clearly here we have 2 players. So the players are player 1 and player 2. Next component of the normal form game is the set of actions. What are the actions here? Once again, here it's easy to see. There are 2 actions for each player. Either they can confess or they don't confess. So with that, let us draw the payoff matrix. 2 players, player 1 and player 2. Their actions are C for confess and D for don't confess. Both of them have the same set of actions. Okay. Let us spend a little bit of time looking at how to fill up the payoff matrix from the statement of the game. So I've color coded this. Let's look at the green font first. So it says if one of them confesses the crime and the other does not, the confessor will be freed while the don't confessor gets a term of 3 years. Let's suppose that player 1 is the confessor, so it plays C, so we're going along this row, and player 2 is the don't confessor, so we're going along this column. So we end up along C and D here at this cell. And at this cell, the game statement says the confessor will be freed. Player 1 was the confessor, so freed means it gets a term of 0 years. And the other person, which is the don't confessor, gets a term of 3 years. That's why player 2's utility is -3 here. Similarly, you can see that when player 1 plays D and player 2 plays C, player 1 gets a term of 3 years and player 2 goes free. For the red font, Both of them confess the crime. So player 1 is playing C and player 2 is playing C also. And then their utilities are -2 and -2 corresponding to a 2-year term. Finally, when neither confess the crime, that is, both are playing D and D respectively, then the utilities are -1 and -1 corresponding to a 1-year term. Fine. So we get a payoff matrix now. Let us now analyze this payoff matrix and see how each player calculates the Nash equilibrium of the game. Okay, so this is the payoff matrix again. Let's analyze this from the perspective of player 1. So player 1 says, I don't know what player 2 is going to do. Why doesn't player 1 know? Because remember, this is a simultaneous move game. Like we said in the last part, simultaneous move game means both players are taking their actions at the same time. It's not that one player is moving first and the other player is seeing that action and then taking its action. They're both moving at the same time. So coming back, player 1 does not know which action player 2 is taking, C or D. So it goes about reasoning. Let me suppose that player 2 is playing C. So player 2 is going down this column. So in that case, for me, which action is better? Do I get a higher utility from C or do I get a higher utility from D? Well, clearly, if we are playing along this column and we are looking at the utilities of player 1, C gives a utility of -2, which is better than D's utility of -3. So player 1 says, given player 2 is playing C, I am better off playing C as well. Next step, player 1 says, now let me see what happens when player 2 is playing D. So we are now going down this column. Same reasoning from player 1, which gives me higher utility, C or D? And in this case too, player 1 sees that playing C gives player 1 a higher utility of 0 than playing D, utility of -1. Okay. So in both cases, player 1 reasons, irrespective of what player 2 is playing, C or D, I'm always better off playing C. And player 2 would reason in a similar manner, since the game is symmetric. And in that case also, player 2 would come up with the reasoning that it's better off playing C. Just for player 2's reasoning, keep in mind that player 2 would keep the row fixed and then it would see which am I better off over, C versus D. For example, keeping the row C fixed, player 2 would see, am I better off playing C and ending up with -2 or playing D and ending up with -3? Clearly playing C when player 1 is playing C. So that's why player 2 reasons, when player 1 is playing C, I'm better off playing C also. And likewise, when player 1 is playing D, it's better off playing C. Okay, so this gives us both players end up playing C, C. So in effect, what each player is calculating is what's called a best response to the actions of its opponent. So P1 is calculating best response to each possible action of player 2, and likewise P2 is calculating for each possible action for player 1 a best response. Okay. So the crux of the matter is the best response, which is irrespective of what my opponent is doing, I will select this action. Now, this is the underlying concept of Nash equilibrium, and if you have realized, this is a very powerful technique. Why is that? Because remember, these players had no way of pre-coordinating. This was a simultaneous move game. They did not know which action the other player was going to take. So there exists no prior coordination. But despite having no prior coordination, they are able to converge on the same joint output of the game, same joint action of the game. Okay, so which is really powerful, because without pre-coordination, you are end up converging on the same output. So without having coordination, you end up getting coordination. And that is the power of game theory and Nash equilibrium as well. Okay. So at this point, I will give the formal definition of Nash equilibrium. It says on the first bullet, a joint strategy S1 star S2 star is a Nash equilibrium when each player is playing a best response. So in this, S1 star is the strategy that player 1 plays, S2 star is the strategy that player 2 plays. Now, I have not introduced the term strategy. For the time being, let's just assume that a strategy is identical to an action. Okay. So what this statement would mean that when player 1 plays S1 star, player 2 can do no better, cannot improve its utility by playing anything other than S2 star. And similarly, when player 2 plays S2 star, player 1 cannot improve its utility by playing anything besides S1 star. In other words, when player 1 is at S1 star, player 2 must remain at S2 star. And similarly, when player 2 is at S2 star, player 1 must remain at S2 star. In other words, this is a stable outcome. They do not have any incentive to deviate. They will not improve their utility by deviating from this joint outcome S1 star S2 star, joint actions S1 star S2 star. So this is the Nash equilibrium, and this is a stable outcome. Once again, this ties back to the fact that without pre-coordinating, without telling each other what action they're going to take, they have been able to arrive at a stable joint action of the game. So this is what Nash equilibrium gives. Now, one important point to remember is that even if we interchange the rows and columns, even if we change the utility values, as long as we keep the relative values of the utilities the same, even if we do these changes, the outcome of the game still remains the same. It's at CC. You can check with this payoff matrix out here. This is once again the prisoner's dilemma game, but I have changed the utility values while keeping their relative values same, and I have interchanged the order of the columns. Okay, so the takeaway is the representation of a game does not change its outcome as long as the relative utility values remain the same. Then you could also do another check, which is we already went through the payoff matrix to check that CC is a Nash equilibrium of the game. You could check all the other joint actions CD, DC, and DD. And here I have solved DD. And here you will see that both for player 1 and player 2, DD is not a best response. So it will not end up being a Nash equilibrium. I have given a few more examples of games, payoff matrices, and you can work out the Nash equilibrium, calculate the best response of each player, and see that it corresponds to the Nash equilibrium. And I have also marked here. This is the Nash equilibrium. Two more games. The game on the left side is the bridge crossing example we are looking at a few portions ago. Another game tag here. Both of these have two equilibria. So in bridge crossing example, the go, stop, and stop go are the Nash equilibria, and in this one, stag, and here are the two Nash equilibria. Another game, common payoff, once again two Nash equilibria here. And finally, Battle of Sexes game, a very well-known game, which says that husband and wife, two players, they have certain preferences over the choices. Husband prefers going to football game, wife prefers to go to the opera, and they dislike either of those, but they like each other's company. So this is the payoff matrix, and once again these two will be the Nash equilibrium, FF and OO. You can try those later on. So let me wrap this up by saying that Nash equilibrium is a very powerful tool in game theory. It allows us to arrive at a stable outcome of the game without having any pre-coordination between the players. Another very important thing that we will talk about more in the next part is that Nash's theorem says that every game is guaranteed to have a Nash equilibrium. In other words, no matter how many players, no matter how many actions, you will always be guaranteed to end up at a stable outcome of the game, which is a very useful result in game theory. Okay. So that's the end of this lecture. Thank you. In this part of the lecture, we'll talk about mixed strategies and Nash equilibrium. We will start with another commonly studied game. It's called matching pennies. Matching pennies is a zero-sum game. In a zero-sum game, if you look at the payoffs or utilities at each joint outcome, you will see that they add up to 0. Hence the name zero-sum game. What that means is, in a zero-sum game, the gain of one player comes at the expense of loss of its opponent. So the statement of the game goes like this. Two coins are tossed at the same time. Both turn up the same face, either heads or tails. Then player 1 wins $1 and player 2 loses $1. On the other hand, if each turns up with a different face, then player 1 loses $1, whereas player 2 wins $1. So if I translate that game statement to this payoff matrix, these are the values that I will get. 2 players, each with actions H and T, and these are the payoffs as defined by the game. Now, if you analyze this game in a manner similar to what we did for Prisoner's Dilemma and try to find a Nash equilibrium using best responses of each player, what you will end up with is quite surprising, which is you will see that there is no Nash equilibrium of this game. Now, that seems to contradict the Nash theorem, which says that every game must have a Nash equilibrium. So, what are we missing out here? Well, the thing that we are missing is called strategy. Okay. So, a strategy is basically a probability distribution over the action set of a player. For example, if you look at the matching pennies game again, and let's say P1 plays H with probability 70% and T with probability 30%. And let's say P2 plays H with probability 60% and T with probability 40%. So in this case, what each P1 and P2 are doing is they are defining a probability distribution over their actions. Okay. So this is called a mixed strategy action profile. It's written as 0.7, 0.3, that is the probability distribution over P1's actions, 0.6, 0.4 being the probability distribution over P2's actions. Okay. An action can also be looked upon as a strategy. For example, P1's action, for example, H is an action of P1, and P1 playing action H is similar to P1 selecting H with probability 1 and T with probability 0. So in this scenario, in which a player selects only one of its actions with probability 1 and the rest of its actions with probability 0, that is, does not select them, so that situation is called a pure strategy. So henceforth, instead of saying that a player chooses actions, we will say that a player chooses a strategy, assuming that selecting an action is a type of strategy called a pure strategy. So now let's revisit the Nash theorem and look at its proper statements. So the Nash theorem basically says that every finite game must have a Nash equilibrium, either in pure or mixed strategies. We saw that matching pennies does not have a Nash equilibrium in pure strategies, but it does have a Nash equilibrium in mixed strategies. At the other extreme is our earlier game called Prisoner's Dilemma. Prisoner's Dilemma does have a Nash equilibrium in pure strategy, but it does not have a Nash equilibrium in mixed strategies. Most other games that are studied, the smaller games, 2x2 games, most other games have Nash equilibrium in both pure and mixed strategies. For example, the Stag Hunt game or the Battle of Sexes game, they have both pure and mixed strategies Nash equilibrium. Okay, so then moving forward, what we want to do is find out a way to determine the mixed strategy Nash equilibrium. Okay, so let's reason this once again from the viewpoint of each player. So a player says, I do not know what my opponent is going to play. Remember, it's a simultaneous move game. They don't coordinate their actions beforehand. But the player also reasons that my opponent selects one of their actions over another because that selected action gives a higher utility than the non-selected action. But I can make my opponent not prefer one of its actions over another. And I could do this by making the utility that my opponent gets from both actions equal to each other. So I take away the choice from my opponent. And I could do this by choosing probabilities over my own actions. So what this would end up making is that the opponent will not have incentive to deviate from one action to another because its utilities from both actions are identical. So no preference of one action over the another. So in effect, this ends up giving a Nash equilibrium or a stable outcome. So the crux of the matter is that in order to determine a mixed strategy Nash equilibrium, each player randomizes or defines a probability distribution over its own actions in a way such that its opponent choice becomes independent of their actions. Okay. Let us now see with an example of the matching pennies game, how we can calculate the mixed strategy Nash equilibrium. So this is once again the payoff matrix of the matching pennies game. What P1 tries to solve is what probability distribution or what probability should I play H and T with so that my expected utility is independent of whether P2 plays H or T. Let's suppose P1's probability distribution mixed strategy is such that it plays H with probability P and T with probability 1 minus P. Okay, so P and 1 minus P. Okay, now given that, let's get into P2's shoes. So P1 is now getting into P2's shoes and calculating what utility would P2 get for each of its action. So P1 reasons, when P2 is playing H, P2's utility will be -1 times P, because this row is played with probability P, -1 times P plus 1 times 1 minus P, which is this expression out here. So this is utility to P2 for playing H, column H, and this simplifies to 2P minus 1. Likewise, P1 calculates what utility is P2 getting when it plays column T, and that works out to be 1 times P plus -1 times 1 minus P. This expression out here, which simplifies to 1 minus 2P. Now, as the final step to find its mixed strategy, P1 solves for P to make P2's utility from its two actions H and T equal to each other. And these utilities for P2 from H and T are these two expressions, 2P minus 1 and 1 minus 2P. So what P1 does, it solves for P to make these two equal. And this is just a linear equation, easy to solve. And if you solve this, P comes out to be 0.5. So P1's mixed strategy is play H with probability 0.5 and T with probability 0.5 as well. And likewise, P2 solves a similar problem. Let's say its probabilities over H and T that it wants to solve are Q and 1 minus Q. And similarly, solving for P1's utilities from H and T and making them equal, it again gets Q equal to 0.5, 1 minus Q equal to 0.5. So the mixed strategy Nash equilibrium works out to be 0.5, 0.5 for player 1 and 0.5, 0.5 for player 2 as well. So I have given a few more examples. So this is called a meeting game in New York. Once again, I have solved this partially for player 1 called player T, and its mixed strategy is 1/11th, 10/11th. You can solve the remainder of this game for player 2 strategies. And then remember Battle of Sexes game, it had a pure strategy Nash equilibrium at FF and OO. Turns out it has a mixed strategy Nash equilibrium as well. I have solved this here on the slides too, and you can go through this later, and you will see that the mixed strategy is 2/3, 1/3 for the husband, player 1, and 1/3, 2/3 for the wife, player 2. Note here that if I change the utility values here, the values of probabilities in the mixed strategies will change. So for example, if I change this to 3, 1 and 1, 3 respectively, probabilities, I think they become 2/5 and 3/5 or something like that. So in this portion, we saw how to calculate mixed strategies. Basically, mixed strategies are probability distributions over the actions, and they are also stable actions or Nash equilibrium. Okay. So in the rest of this lecture, we will quickly look at a few software that can be used to solve Nash equilibrium. Finally, I have given another game, rock, paper, scissors. This is a 2-player game, but each player has 3 actions, or traditional rock, paper, scissors game. It does not have a pure strategy Nash equilibrium, but you can solve it and see that it does have one mixed strategy Nash equilibrium. Okay, so that's up to you to solve. Fine, so let's conclude this part, and in the next part we'll look at software for playing game theory. This is the last part of the lecture on game theory, and here we will discuss some game theory software. The main solution concept that we looked at for games was Nash equilibrium. Nash equilibrium can be solved using a math problem called mixed integer linear program, MILP for short. MILP basically is an optimization problem with linear constraints, with the limitation that one of the constraints must be an integer. There are commercial solvers called Gurobi and IBM Simplex. They're very fast MILP solvers, but they're free for academic use. I have used an open source library for solving MILP that's called CoinOR. It also comes with a Python interface called CYLP. This is the website for downloading CoinOR. Now these are libraries that you can use to solve math programs for finding Nash equilibrium. Now there are a bunch of software which are available which have algorithms for finding Nash equilibrium and other types of equilibrium and solutions for games. So we'll discuss some of them. First is Gamut. Gamut is actually a library not for solving games but to generate games. You can vary the number of players, actions, also different types of games that you create. Gamut is a jar file. So you download this gamut.jar file and you run it from command line using java-jar switch. Let me show you in a bit on the command line what it looks like. So here I have a command java-jar gamut.jar and I'm creating an instance of the Battle of Sexes game and outputting it to boss.txt. So when I hit enter, the bos.txt file has been created, and let me open that and show you. So this is the payoff matrix that's there for the different joint actions. Now the good thing about Battle of the Sexes is that every time you run it, it randomizes the seed and creates a new instance of the game. So I ran it again and now you see that the payoff matrix is a fresh one. This is very useful if you have to generate a large number of instances of the same game for experimentation or something. It's very difficult to do it by hand. So you can use this tool and you can generate, every time you run this, it will generate a new payoff matrix for the game. There are 35 possible classes of games inside Gamut. The standard games that we have seen, Battle of the Sexes, Matching Pennies, Prisoner's Dilemma, Stag Hunt, all of them are there, and several other games are there too. So that's one of the libraries to play around with. The next library, important one, is Gambit. Gambit basically provides an interface to input a game and also interface options to solve the game. So here is Gambit. So I click this icon to create a normal form game. It fills it up with the default 2x2 game, and I can input the payoff matrix values. So let me input here the Battle of Sexes game. So 1, 2, and 1, 2. And then I hit this button out here to solve for Nash equilibrium. Asks me whether I want one Nash equilibrium, all. Select all Nash equilibrium. And it outputs all Nash equilibrium, 2 pure strategy Nash equilibrium and 1 mixed strategy Nash equilibrium. It outputs it here. So this is very flexible, very fun. You can edit the names of the actions, add more players, create larger games, and solve for Nash equilibrium. Okay, so this is an interface, very useful to use. But suppose you want to write your own code from which you generate a game inside that, give it or give numbers for the payoff matrix inside it and solve it. So for that you need to integrate that with the code that you have written. So for doing that, Gambit is a library. You could use Gambit, but one of the things I have seen is that Gambit is not compatible with Python 3. Gambit 16, the latest version, works only for Python 2.7. So for working with Python 3, there is another software which is called NashPy. And this is the website to download NashPy. And you can just import NashPy into a Python program that you write. And here I have one. So I've just done an import NashPy as Nash and requires NumPy. And here I've just created some 2x2 payoff matrices. Some for like one for Prisoner's Dilemma, one for Matching Pennies, another for Meeting in New York, and finally one for Battle of Sexes. So the last one is the one that I will show to you and solve. So this is the matrix, the payoff matrix we have seen. Create an instance of the game, and then I use a Nash equilibrium algorithm called support enumeration to solve it. And once I run it, you will see that it outputs the 2 pure strategy Nash equilibrium and 1 mixed strategy Nash equilibrium. So NashPy once again is a useful library that you can have in order to write your own code using Python. So that pretty much wraps up our discussion on game theory. I have given a list of resources like the textbook that I used to teach this course. It is written by computer scientists. That's the first one by Shoham Leighton Brown. There are many economics-based textbooks on game theory. I have given the ones which are sort of the introductory texts on game theory. There are many additional resources on the internet available as well. And at the end, I've given some information, additional information slides. Feel free to browse this if you want to know some fundamental things, a bit advanced about games. Okay, so I will stop here for today, and feel free to ask any questions in the time that we might have.